Likewise, we define V2 is equal to set of all elements or vertices in a vertex subset such that the distance between the 2 points, say V and V1, is of odd length. So this is what you have in your notebook. I say to prove the converse. Conversely, if all my cycles in this graph G is of even length, and if my graph is going to be connected, then let us construct the following. For any point V1, it is small v1, V1 in capital V, define a vertex subset capital V1 is equal to set of all elements in V, D of V comma V1 is even. Similarly, capital V2 is equal to set of all V in V, D of V comma V1 is odd. What is my observation? So from the graph, we partition into V1 and V2. V1, all my edges of even length. V2, all my edges are odd length. So what can we think about V1 intersection V2? So now the elements in V1 are different. The elements in V2 are different. So V1 intersection V2 will definitely become empty because there is no common elements, intersecting elements between V1 and V2. As such, V1 union V2 will be nothing but the entire set V. So this is what you have here. In this case, clearly V1 union V2 is V and V1 intersection V2 is empty. What I am going to prove now, having in mind, we have to prove that graph is bipartite. In such a kind of V1 and V2 set, we have to prove it is a bipartite graph. That is to prove that there is a line joining from the set V2 to the set V2, from the set V1 to the set V2. Now, to prove this, we are going to use the method of contradiction. I have to prove the graph is bipartite. That is to prove there is a line joining from V1 to V2. So the moment I say it is a bipartite, more than having a line from V1 and V2, the other ancillary character of a bipartite graph is there is no adjacency in the same set. This is an important nature of a bipartite graph. There will be no adjacency in the same set. So if I have a bipartite graph, this nature is obvious. You will not come across any adjacency in the same set. There will be no adjacency in the same set of V1. There is no adjacency in the same set of V2. If this is going to happen, then it is going to be a bipartite graph. So we are going to prove this theorem in a controversial way. So I am going to say that the graph is not bipartite graph. Then we will result out in a contradiction. To say the given graph is not a bipartite graph, I need to say rather there exists an adjacency between the same set of elements. Suppose there exists an adjacency in the same set of a vertex subset. Whether there exists adjacency in a V1 itself or an adjacency V2 itself, having a cycles of even length will definitely contradict our assumption. This is what we are going to prove now. So let us assume whatever the assumption I do, it is enough if I am going to do for one subset. So we are going to assume that, let us assume that there are two vertices, say U comma V, are adjacent to each other, are adjacent in the vertex set V1. So the argument I follow for V1 at the end will be true for V2 also. So let us consider only for this the argument vertex V1 and see how it is going to contradict our fact. So having this in mind, we are going to say that we shall now prove that every line of G joins a point of V1 to a point of V2. This is what we have to prove. So when I prove this, automatically it is understood there is no adjacency on the same vertex set. Because I have to adopt the method of contradiction, let me say G is not a bipartite graph. That means it is not going to have a line joining from V1 to V2. That is to say that in the same subset of a vertex set, either among V1 or among V2, there will exist some 2 points adjacent. So this is what my assumption in a contradiction be. I have to prove G is bipartite. That means there will be a line joining from V1 to V2. This is what I have to prove, which means there is no adjacency on the same vertex set V1, followed by then V2. I am going to apply the method of contradiction. Let suppose G is not bipartite. That is, let's suppose there is no line joining from V1 to V2. Let's suppose that is among the one of the vertex subset, there is an adjacency between the element. There exists an adjacency of the vertex in the same vertex set. If suppose this is going to happen, we'll see what is be the result. So I say suppose 2 points u comma v in V1 are adjacent. Then we will be able to have a picture of the following form. How is it? Assume that there will exist an adjacency between the point u and a point v. All happens in the same vertex set V1. Then having this in mind, vertex set V1, this in mind, we are going to construct a picture. What kind of picture? Because our subset vertex set V1 as well V2 has got a shortest path, we were defining a distance between the 2 points. So because the graph is a connected graph, we are able to find a shortest path. So let us say there exists a shortest path, say P and Q, in the vertex subset V1 for the respective figure, such that P is the shortest path, say from V1 to U, whose length is going to be the value m. Shortest path length is m. Likewise, Q is the shortest path from V1 to V, whose length is n. This is always possible. As it is a connected figure, shortest path exists. One can have a path of this form. So I say let us have V1 to U. So I have U already. Say a point V1. Say V1 to U is a path P. V1 to V is a path Q. This is always possible because we have considered a connected figure for our discussion. So we say let P be a shortest V1 to U path of length m and Q be a shortest V1 to V path of length n. So this is the shortest path, say P, whose length is m, and this is going to be Q of length n. One can have, say, a path, one may be in a position to have something, say, a common point. There is a possibility of having a common point in any path it exists, such that because it is a connected graph, more than a path, we are able to always come across many walk in it. So it is always possible to have even a common point in it. Suppose if there exists such a kind of common point in a considered figure, we'll see how it is going to result out. So they also say that our discussion is only for the vertex at V1. The length m and the length n are found to be even quantity, even numbers. So going back to our given statement, our given statement is for a graph G which is connected consisting of a cycle. When it has a cycle, it is of even length. This is what given to me. So the moment it is going to form a cycle, this analysis will become true. So let us have in our backup mind this assumption or the analysis is always true. So apart from that, because I have to prove it is a bipartite graph, because I adopted the technique of contradiction, I say if suppose G is not bipartite, then this fact will become false. This is what we are going to prove it. So as I made in the same vertex set U and V are adjacent, there is a possibility of having a